Hey folks, alright, well, last time we promised that next time we take a look at a little tree walking algorithm to go through and try and produce code from our abstract syntax trees or from some kind of a parse tree representation of things. So that's what we'll take a stab at today and see how we go. Alright, again, the idea is we've got sort of some kind of a syntax tree that's just this giant collection of nodes that represents the program as a whole. And so, in general, we've got the program made up of these kind of higher level components that's made up of a bunch of things, and those are each made up of a bunch of things, and those are each made up of a bunch of things. And so what we'll do is, in the beginning, we'll take it from the perspective of just expressions. So let's say we've got an expression representing something, and we'll take a look at how to walk the tree that represents that expression and produce code that implements that expression, if you like. So we'll start with simple expressions, primitive operators, and then we'll start expanding to more and more fancy things and fancier data types and fancier operations. And again, the idea is we're going to come up with some kind of a recursive function where you give it a node in the tree and it produces the code for essentially everything from that node on down. So if the node represents an assignment statement, it'll go through and, on the left-hand side, produce the code for whatever the variable is, produce the code for the operator itself, and then go through the right-hand side and produce the code for the expression. But we've got some kind of a way of producing this stuff. So what we'll take a look at is actually a kind of bottom-up approach where we'll evaluate the two subtrees, and then based on what they produce, we'll evaluate the result, but we'll get there. I'm just going to kind of make up an set of assembly language instructions as we go through this. Kind of as we need stuff, we'll make up something for it. But the ideas should map to just about any kind of reasonable assembly language that we wind up working with. So we'll start off with a nice simple example, simple expression. We'll assume our normal precedence and associativities. So if we say x plus y times z, then we're talking about doing the y times z first and then adding x. So if we were thinking of the abstract syntax tree, we'd have the plus as the root, we'd have the x on the left-hand side, we'd have the multiplication as the right child of the plus, and then y and z would be the two children of the multiplication. So nice simple tree. And if we were going to go through and do a sort of post-order traversal of this so that we process the operation last, right, go evaluate the two subtrees and then evaluate the operation, then the post-order traversal would go through and it's going to do the left subtree, so it's going to get that x, and it comes up and then it goes down to do the right subtree, and so it's going to do the left subtree of that, so it gets the y, and it's going to do the right subtree of that, so it gets the z. Then it finishes off this subtree and gets the multiplication. Then it winds up going back up, and now we do the root and we get the plus. So post-order traversal, we get the x, y, z times plus. And again, this kind of supports a sort of bottom-up evaluation of what we're going to do. So in the expressions, the idea is we want to come up with sort of a result for the left subtree and a result for the right subtree and add them together. So since we're thinking in terms of registers, I want to go through and produce whatever code is necessary to get x and wind up with that in a register. And we'll have our tree walker turn around and say, okay, here's the register that, the result of this wound up, effectively the result that, or the register that x wound up in. And when it goes through to parse the right subtree, or to process the right subtree, it goes through and generates whatever code is necessary to do the y times z and winds up with the result in a register. So when it returns up here, it says, here's the register, I put the result from that in. And then my plus operation can work on those two registers and stick in the assembly language instruction to say, okay, well, add this register to that register and, return the result to whatever this is the subtree of. So this is the idea. Our processing is going to go through, produce code to get x into a register, produce code to get y times z into a register, and then produce code to use those two registers in our addition statement. Now, a few things that we have to consider. we've got this idea of an activation record, sort of our stack frame, if you like, that's got the all of the data values for our current function call. We might have a global variable section somewhere out there. And most of the things that we're working with are expressed as offsets from the starts of these different locations. Right? Stuff that's in the heap we might have an absolute address for. But when we're going through producing code, the code that we produce is going to depend a bit on whether the things that we're working with are local variables, global variables, whether they're stuff off in the heap. And so I'm going to assume that we've got a register, and call it whatever you like. Let's say RA, a register that's got the address of the activation record. And then for each of our local variables, I'm going to assume these are locals for now. For each of our local variables, we've got them recorded as just an offset from the start of that activation record. So when I actually want to get X and put it in a register, the value of X, then I have to take the address of our activation record plus the offset for X, and then go to that memory location, grab whatever is there, and stick it in a register. So we're going to assume that nothing is in a register yet, other than RA, and we're going to go through and look at code to get X, Y, and Z out of memory into registers, and then produce the desired result. So that's our idea. So again, I'm making up instructions as we go here. So I'm going to say I can load the offset of a variable into a register. So I'm going to call that one load A. So we'll load X's offset into R1. And then I'm going to use a load instruction to actually take the content at some register plus some offset and stick it someplace else. So here we're getting X's offset, putting it in R1. Here we're taking the activation record's address, adding the offset for X, going off to memory, grabbing whatever's there, and sticking that in R2. So this is the process that we're going through to get X out of memory and stick it in R2. And then we'll do the exact same process to get Y out of memory and put it in R4, and the exact same process to get Z out of memory and stick it in R6. So now we've got R2 is X, R4 is Y, R6 is Z, and we can carry out the multiplication first. So we'll take R4 times R6 and stick it in R7. So now we've got the result of that subtree. And then we want to take that and add X's value to it, so the R2 and R7. And again, we'll stick that in R8. So we're just making up register names as we need here. So this is the kind of code we would like to see our tree walk produce, other than the comments. So we want our code to be able to do things like generate the instructions to load our variables from memory into registers, and to take registers and multiply them together and stick the result somewhere, or to add them together and store the result somewhere. So this is the kind of thing we want our tree walk to do. So as it was going through that post-order traversal, remember we said it was going to do X, then Y, then Z, then times, then plus. Right here we've got the stuff for X. Here we've got the stuff it would be producing for Y. Here we've got the stuff it would be producing for Z. Here we've got the stuff it would be producing for times. And here we've got the stuff it would be producing for plus. So we just have to think about what our tree walking algorithm might look like. Again, we want something that's going to perform this traversal of our abstract syntax tree and output the result. We're assuming the values are stored in registers. So we have to get if we refer to a variable, we have to get it out of memory and stick it in a register. When we're going through this process, we have to be able to tell, well, geez, have I already loaded X into a register or not? If it's already in a register, I want to use that. Right? I don't want to create another X that's in another register someplace, because then things are just going to get confusing, as well as wasting registers. So we'll assume that we've got some kind of a way to look up, is X in a variable right now? And for the moment, I'm going to keep it simple and assume that we're just talking about binary operators in our nodes here. So things like plus and minus and divide and times, that kind of idea. And the values that we're working with are either just straight numeric literals or variable names. And we'll deal with all the other gory details later. And I'm also going to make an assumption that we've got some output function where I say, here's the operator, here's the couple of registers, here's where the result should be, here's the register the result should go into, produce the right code. And that's basically just going to be some grand glorious switch statement. So let's take a look at a first stab for our tree walker. So we give it a node in our abstract syntax tree, so I'm just node n, and I'm just going to call my routine walk. And again, what we're going to need are variables to hold the names of the registers we're working with. A register that I'm going to put the result in, a register to hold the left subtree result, and a register to hold the right subtree result. And then I'm just going to look at what kind of a thing n is. Is it an operator? Is it a variable name? Or is it a numeric value? So if it's an operator, if n is an operator, then I want to go off and process the left subtree, and that's going to put a result in one register, so I'll save, it's going to return that register name to me and say, okay, well, whatever register you stuck your result in, I'll store in temp1, right? The name of the register is going in temp1, and whatever register you store the result of processing the right subtree in, I'll store that name in temp2. And then I'm assuming we've got some kind of a routine that will tell us what the next available register name is. So we'll call that and say, okay, well, give me a new name, and I'm going to put the result in that register. So then we'll call this output routine that we were talking about and say, here's the operator, here's where the left subtree's result is, here's where the right subtree's result is, right, the two register names, and here's the register name to put my result in, generate the code, right? And so that's going to be the switch statement that says, okay, well, if the instruction was a load, we'll do this. If the instruction was a mult, we'll print out this. If the instruction was an add, we'll print out this. And all it needs to know is what kind of instruction it was and what the two operand variables were and what the target result is, or what the destination register is. So we've got a routine to run if it's an operator. If it's a number, then all we have to do is figure out what value it represents, what literal value it represents. So maybe we'll get a register for the result. We'll say, okay, well, I need to do some sort of a load immediate to get that literal value into a register. So give me the literal value from that node, use a load immediate, there's no extra operand needed in this case, and we'll put the result in this register, whatever it was called. And otherwise, if it's an identifier, like the example we looked at a moment ago, then we'll say, okay, well, get the base address that this thing is coming from, is this off the activation record, for instance, get the offset to it from that base address, get the name of the next register where we're going to store our result, and then call our output thing and say, okay, you need to load this variable, right, based on this base address and this offset, and put the result here, put the content here. Right, so we can come up with a reasonable tree walking routine. Now again, this is only set up to handle binary operators at the moment. Binary operators, numeric literals, and variable names, identifiers. But we could keep expanding this to get more and more flexibility, start adding unary operators for things like x++, or unary operators for things like ++ x, and continuous and ternary operators, and all the different wonderful things that all the different data types we might wind up working with. So again, we've got this output function that we're assuming exists that takes an operator, 2 arguments, and a destination register. And it's basically just going to be some grand glorious switch that says, okay, well, if it's this operator, then here's the output syntax for the 1 or 2 or 3 assembly language instructions we have to generate. Right? Plugging in the argument names where they belong, plugging in the destination register name where it belongs, and it should be reasonably mechanical, although it might be kind of lengthy. And again, we can expand this tree walk as much as we need to get the different kinds of operators into it. All right. Now, in terms of loading from registers, we talked about this a little bit earlier. If they were already in registers, then we don't want to load them again. So we might access a lookup function to make sure, okay, well, does this thing already exist? and we might have to tweak things if we're referring to things that are in the global variable space as opposed to our local variable space. It might be a little different. If it's in the if we're accessing something that's off in the heap, again, that's going to be different still. So there are some tweaks to this that are going to have to be made, and those might come in terms of our output function, right? Just different things that we have to do, or they might involve tweaks to both the output function and the tree walk. A couple of things to mention. Pass-by value parameters we can probably handle pretty much like the variables, right? Just thinking in terms of, okay, well, this thing's going to be at some offset from the start of our activation record. For pass-by reference parameters, again, if we know it's already in a register, we can go ahead and use that, and with the assumption that it's going to get put back in memory sooner or later. But if it's not, then we've got this extra step that we have to go through, because we've got to get the value of the parameter, which is likely to actually be a reference or a pointer to where the actual value is in memory. So we've got to get the offset and the base address for the activation record. Those give us the address of the parameter, and then that parameter contains a pointer that's the actual address in memory that we have to go to load that. So we do have the extra step that we have to consider for things like pass-by reference parameters. Now, we've been making up new register names for this as we go along. One of the objectives is generally to try and keep that register count down to some sort of reasonable level. So if we can, we would rather reduce the number of registers rather than just grand and gloriously keep piling on. So one of the things we can do to at least keep it down somewhat is to think about the order in which we process the subtrees. Now, while we're going through and using all these temporary registers, when we don't need a register anymore, it can be freed up, and that name can effectively be used again. So that get next register can be keeping track of that kind of information. So if I've got two subtrees that use different numbers of registers, right, as I go through and process one subtree, I can go through and do it uses 5 registers, let's say. Then I have to remember the result for that in a register someplace and process the other subtree. So let's say I've got one subtree that uses 5 registers, one subtree that uses 3. If we do the larger one first, if we do the one that uses more registers first, then we use 5 registers while it's going on, and then while we're processing the other one, we've got the one register that's remembering what was in the left subtree, and we use 3 more to process the right subtree. So as that's going on, we're using 4 registers. So 5 registers during part of this, 4 registers during part of this. If we do it the other way around, if we do the little one first, then we use 3 while it's going on, and then we've got the 1 to remember it, plus the 5 while we're processing the left subtree, and so at one point here we wind up using 6 registers. So if you always first do the subtree that requires more registers, then we can at least cut our register count down, our maximum register use down by some. And again, as this mounts up as the as we think of this huge tree where we've got all sorts of different disparities between what left subtrees and right subtrees are doing. But this assumes that before I go through to process them, I know which subtree is going to use more. So what's often done is to say, okay, well, we'll have a little kind of preliminary tree walk. So we'll have a little mini tree walk that just goes through and tries to count how many registers each subtree is going to use. So it does that first traversal and says, okay, here, now we know how many they're each going to use. Now we'll do the real tree walk where we actually go through and process things in a valid order to try and minimize the register counts as we produce code. So that is something to keep in mind. And one of the other things that I wanted to kind of introduce here is the idea that we would like our compiler to be reasonably smart about optimizations. If you've got an expression like a plus b minus c plus a plus b, then if we think of things purely in terms of the order of operations dictated by our source code language, or our target language for that matter, then we're going to be going through and saying, okay, well, I have to do this plus first, and then I have to perform the minus, and then I have to perform the next plus, and then I have to perform the next plus. Now, any human looking at this is going to say, oh yeah, but I've got, a plus b twice here, and I know it's not going to change the result. I can do these operations in a different order, so I can do my a plus b, double it, and then do my subtract c. And if we're thinking of terms of storing the subtree results, then I'm only storing the result for a plus b once, then I'm doubling that, and I'm subtracting my c. A lot of compilers are smart enough to go, gee, if you want to double something, then the efficient way to do that is not to multiply it by 2, it's just to do a bit shift left by 1, and bit shifts are really efficient operations. So really what I want to do with this is to take a plus b, do a left shift of, oops, that should actually be a left shift of 1, do a bit shift on it, and then subtract c. So our compilers should be able to look ahead somewhat, to look at our expressions, recognize common sub-expressions, and try and perform reasonable optimizations on that. Now, there are some things that are also going to have a big impact on this if we've got a, as we'll talk about in the next section around, if we've got something like a function call in here and the function could have side effects, then that might mess up our ability to try and perform optimizations on this. Or maybe I've got a function call in the middle here that could modify b. Then I can't reuse this second a plus b because that one might have changed because of this function that ran in the middle. So we've got some things that are going to interrupt our ability to do this. There are times when, even if I've just got a slew of addition operations, the order that I do them in can make a difference. If you think of floating point numbers and the limits of precision in floating point numbers, if I've got a whole bunch of really small values and some really big values, if I start with the big value and start adding the small values in, they're not going to be significant enough to change the value. So if I've got a big value a and I add a little tiny value b, the result is still going to be a because b is kind of off the lower bound of the precision for a. On the other hand, if I start adding together the little tiny ones, I add 10 or 20 or 50 different little tiny ones together, then by the time I've added them all together, they might be big enough together to make a difference in adding them to our larger number. So the order of operations can have an impact as well. Or it might be something like if you're doing a plus b minus c, if you do a plus b, you might get overflow. But if you do, say, a minus c and then do the plus b, it might all fit. So there are certain things that we have to be aware of when we're thinking about the order that we perform optimizations or perform operations in. All right, those are all things we want to come back to and revisit more.